In this video, we will study the conservation of mechanical energy and its application. Now, this is a continuation of the video series of starting from the work done by the force. Then in video number 2, we studied the work done by gravity. Then in video number 3, we studied work done by elastic force. In video number 4, we studied the work energy theorem. We will use everything we derived in the last videos. So we will study the conservation of mechanical energy, and we will solve problems that involve the conservation of energy. If we consider an object, let us say an object starts from that point 1, then traveled at point 2. So from this point to this point, object traveled with displacement. So therefore, there must be energy on top of it, and while traveling, it consumes energy down the plane. So therefore, again, this is a kind of dynamics of motion. If we recall in our video number 4, the work energy theorem, that the work done of this system is just the change in kinetic energy, which means that if the kinetic energy is available, initial and kinetic energy final is available, then take the change of that, the answer is equivalent to the work done by the system. Or if given the initial velocity and the final velocity, and we have the mass, okay, we can find always the kinetic energy, and we can also obtain the change in kinetic energy in such that we are solving the work done by the system. Okay. Now, since we have only gravity, so work done by gravity, take note, in video number 2, the work done by gravity is just the change in potential energy. Okay. Now, if there is spring constant of spring present during the travel, then we can involve the work done by elastic. And work done by elastic is again is negative change in potential. So this is very important. This is true to all potential. Okay. So if we consider only again conservative force, we ignore the effect of the friction or whatever force is present on that. We will consider only the object that travels from point 1 to point 2 by the presence of the gravitational force. We call that as a conservative force. So we can do it by uh, placing this object at point 1, then release freely. So everything, oh, now if this is a frictionless, okay, if this is a frictionless, then we have only the gravitational force present. So therefore, in that case, work done by the system is just equal to the work done by gravity. So we can equate these two. Okay. So work done by the system is, take note, is the change in kinetic energy, and work done by gravity is negative change in gravitational potential energy. Remember frictionless because we consider only conservative forces. It is the gravitational force. So substituting the value of the work done by the system, which is the change in kinetic energy, and the work done by gravity is just a negative change in gravitational potential energy. Okay? But change, take note, is final minus initial. So we can replace that with the final kinetic energy minus initial kinetic energy. And the change in gravitational potential energy is the final gravitational potential energy minus the initial. So remember that we have 2 points. In point 1, we have the kinetic energy at that point. Take note, kinetic energy is the energy possessed by the velocity. And we have also the kinetic energy final. And we have also, at this point, we have the gravitational potential energies, U1, and we have the final gravitational potential energy at point 2. Okay, so we can remove the grouping symbol here. Remove the grouping symbol. So we have now final kinetic energy minus initial kinetic energy is equal to the negative gravitational potential energy final plus the gravitational potential energy initial. This is minus minus becomes plus, and this will be negative. Now take note of the subscript. If we combine terms that have the same subscript, that would happen if we transpose K1 to the other side and U2 in the left side. So do it. We have K2 plus U2 is equal to K1 plus U1. We are combining terms that have the same coefficient or subscript. So therefore, we can say that K1 plus U1 is just equal to K2 plus U2. Now, what is K1? Again, K1 is the kinetic energy initial at point 1. And we have U1. U1 is the gravitational potential energy at point 1. Then, it is equal to the kinetic energy final K2 plus the gravitational potential energy final. So take note. Okay, the meaning of K1 and U1 is the total energy at point 1. And the meaning of K2 plus U2 is the kinetic or the total energy at point 2 in the final point. So when we say K1, K plus U, it is E, the total energy. So E stands for the total energy at that point. So therefore, this will be our E1, while this one is our E2. E means the total energy at point 1. So the energy present during this travel at point 1, we have only the kinetic energy and the potential energy. These are all mechanical energies. Okay, so in the other side, we have the E2 plus U2. So therefore, E1 is equal to E2, which means that the energy at point 1 is equivalent to energy at point 2. This is called as the conservation of mechanical energy. But take note, this is only for conservative forces only. Because we ignore the effect of the other, or let us say friction. We did not include. So energy is conserved. The question is, what will happen if we consider friction now? Okay? Is it the same? Okay. So again, this is energy 1 and this is energy 2. So energy 1 means what? Energy 1 means T1 plus U1, while energy 2 is K2 plus U2. Okay? So therefore, we can utilize this problem if we have only the conservative force present during the travel. Conservative forces are gravitational force. Okay, we have also the elastic force. So therefore, we can say that again, the total energy initial is equal to the total energy final. This is conservation of mechanical energy because our energy present here is all for mechanical energy. But we can use the other form of energy. Energy, take note, cannot be created nor destroyed, but we can transform the energy from one form to another, which means that the potential energy can be converted to kinetic energy, vice versa. Kinetic energy also can provide the potential energy because energy is conserved and it cannot be, or it can be transformed from one form to another. Okay, now what will happen if we consider all external forces on the object? What will be the conservation of energy? Okay, so this time we will consider the friction. This is with friction. Still, we can use this one. Okay, the work done by work energy theorem and the work done by gravity or work done by elastic. Okay, so if we consider all forces or external forces, which means that if we consider all forces present on this object while moving from point 1 to point 2, then our work done by system now becomes not only for the gravity, we will include work done by the other. Now in this problem, this is only work done by friction, but we can apply everything here. If there is a force applied the object downward or a force applied down upward, then we have to accumulate, we have to take the algebraic sum of the work done by that forces. We call that as work done by the other. But again, in this problem, the only present here is the force that affects the displacement is the friction. Take note, the normal force. The normal force does not contribute the work done because the normal force, work done is always zero. Okay? So then, the gravitational force is on the work done by gravity. So we will run this equation. Okay, work done by the system, this without subscript is work done by the system, and this is change in kinetic energy. While this is work done by gravity, and we can replace that with U. And work done by other is, again, this is for work done by friction or other external forces. So leave it as work done by other. So this is change in kinetic energy, a negative change in gravitational potential energy for potential, work done by potential. Then substitute change means final minus initial. So the same K2 minus K1, and U take note is the final minus initial gravitational potential energy plus work done by the other. Okay, remove the grouping symbol and remove the grouping symbol. Then again, almost the same. If you notice, in our previous, if we consider only conservative forces, we ignore the work done by the other. So we just add here terms, the work done by the other. So again, combine all those terms that have the same subscript. So we come up with this result. Or this is the same as the kinetic energy initial plus potential energy initial plus work done by the other is equivalent to the final kinetic energy plus the gravitational potential energy. So therefore, this one, K1 plus U1 plus work on the other is just the total energy at point 1. While K2 and U2 is the total energy in the final point. So E1 is equal to E2. Again, this is the conservation of energy. Where E1 here is the initial and this is E2 as the final energy. So again, this is the conservation of energy considering all external forces, and all external forces are found in the work done by the other. So if you look at the equation, if we expand energy initial is equal to, this is the meaning of conservation, energy is conserved, which means equal. So the energy initial should be equal to the energy final. But take note, if we include all forces, external forces, it can be done only in the initial point of travel. So everything will be accumulated here. So take note that in our video number 1, work done by the other, we can always calculate all forces that acts on the body. So we can use that concept. F is cosine theta. So take note, there are work done that are negative. There are also work forces, ordinary forces that can be a positive, and there is also zero. So again, if you are solving or using this conservation of energy, E1 plus E2, take note, work done by external forces are found in the initial point. It should be in initial E1. So, in the final, do not include the work done by the other or else it can be cancelled. Okay? So, therefore, if your force contributes the displacement, then the work done by that other force is positive. If that force does not contribute, zero. Okay? Or if that force counters the displacement, the work done is negative. So you have to accumulate it here, algebraically substitute in the initial point, then go with your solution. So therefore, again, in the initial energy E1 is K1 plus U1 plus the work done by other, and the final is just K2 plus U2. Now take note, K means the kinetic energy initial. U1 is the gravitational potential energy. Now, what will happen if we have the elastic? Suppose we have the spring at this point. Okay, then include here. You just add this term. This energy now, potential energy is composed of two. We have the gravitational potential energy plus elastic potential energy initial. Then you have to add another term here plus elastic potential energy final. So just add the potential. Okay, but take note, it that elastic will present only if there is elastic activity happens at this point. Okay? So, if you are saying that we have the spring here, then include that point. Now, if there is no spring in the final, then equate that to 0, the elastic energy at that point, because we have no elastic. So, just utilize this formula, then add all energies present in the initial and all energy present in the final. That's it. Then use some definitions that we studied from video number 1 to video number 4. Then go with the process. Okay, so in order to understand, let's apply uh, the problem, and we will solve that using the conservation of energy. Look at this one. The problem says that we have the block of 0.5. Sorry, this is 0.5. This should be 0.5 kilograms. Change this to 0.5 kilogram. Then, uh, okay, and we have this spring of negligible mass. Now, compressing the spring to a distance of 0.2. So, therefore, we compress the spring. Okay. Now, take note, the spring constant is 100 Newton meter. This is given in the problem. K means the force constant or the spring constant. Then, the block was, okay, we compress it in with what? We compress the spring 0.2. Okay, we apply a force, compression force, then it was able to compress a displacement, spring's displacement of 0.2 from the rest position of the spring, or the unstretched level. This is 0. It starts here, then we compress that at 0.2. Okay, then the question is, once we release the object, okay, if we release the object, take note, this object will move towards right. Okay. Now the question is, what is the coefficient of kinetic friction between the block and the tabletop? Which means that you are asked how much is the coefficient. So therefore, if we release it, okay, then it will move at a displacement of what? At a displacement of 1 meter. Okay. So it starts from here. Take note, the mass is 0.5. So this travels horizontally towards right, and it has a displacement of 1 meter according to the problem. Okay. So, question is, how much is the coefficient of kinetic friction? That will be the requirement of this problem. So, we will solve this one. Now, if you remember, in dynamics, we can solve this problem using Newton's law. But take note, this is spring involvement. So, the problems now, the solutions of the problem becomes difficult or complicated solution, but still we can solve. But we can solve this effortless using the conservation of energy. So mu k means the coefficient of kinetic friction. We will solve this problem. So to answer this problem, one method is to use the conservation of energy. Take note, in our previous slide, the total energy initial should be the total energy final. So the question now is, what are the energies, possible energies in initial point, and what are the possible energies in the final point? Okay. So take note, at point 1, we compress this one. So therefore, okay, at point 1, there we have the kinetic energy initial, we have the gravitational potential energy initial. Now take note, we have the spring, so we will include the elastic potential energy initial. And this is work done by the other. Take note, it should be in the first. Now in the total energy final, we have the kinetic energy final plus the gravitational potential energy final. And we have again include the elastic potential energy final. These are the possible energies, but not all are functioning. So we will study the actual problem. The actual problem says that the object moves from here to this one. Now take note that this is horizontal, okay? Then this starts from rest. Okay? So take note, if it starts from rest, the kinetic energy must be 0. Now, in the final point, take note, the object stops moving. So therefore, the kinetic energy final should be also equal to 0. Another is, remember, this is lying in horizontal surface. What will be the that gravitational potential energy is possessed by height. So since this is in level, horizontal surface, if we place the reference line along this object, then there is no height, which means that the gravitational potential energy 1 and 2 are 0. Now take note that the spring is present only in the initial, and we have no spring involvement in the final, which means that our final elastic energy should be 0 also. So we have only two terms. Okay? The terms are the initial elastic potential energy. This is caused by the spring. Then this one is the work done by the other. And take note, we have only one force, external force present while moving towards the final. Aside from the gravitational force, because gravitational force already the potential, we have only the friction. So therefore, work done by the other is done only by friction. Take note, friction is negative, opposing, it is a negative work done. Because it is always 180 degrees from the displacement, so it is opposite. So therefore, it should be negative. So therefore, again, this we have only the elastic potential energy plus work done by friction minus 0 or equal to 0. But take note that again, work done by friction is negative, and it is equal to the frictional force multiplied by the displacement. The displacement is 1 meter, so nothing to worry. X squared, this is what? This is the definition of the elastic potential energy. Kx 1 half kx squared. Remember in video number 4, uh, the elastic potential energy is 1 half kx squared, where x in our problem is 0.2 or 0.20 meter squared, and spring constant is 100 Newton per meter. So therefore, the only problem here is the friction. But take note, what is friction? What is friction? Friction is mu times n. Mu times mu k is what? Given unknown. This is unknown required. While n is the normal force. Now, since this is in horizontal, then the normal force is just equal to mg. Okay? This is in video number 1. The normal force is just mg because this is horizontal. So mu mg is the friction multiplied by the displacement. So therefore, we have now 1 half k squared for the elastic energy minus the mu k, which is unknown, and this is the mg is the normal, so mu n is friction and displacement is s, and equate that to 0. So look at this one. We are asked to solve for what is mu k. So all you need to do is to transpose to the right, then divide both sides by mg is. That's it. You are already solving mu k. So therefore, again, transform the solve for mu k. We have kx squared here divided by 2 mg, because we will divide both sides by mg is. So therefore, we have 2 mg is the divisor. So kx squared plus 2 mg is. Substitute everything. Take note, k is 100. X is 0.20 squared it. Then mass is 0.50 kilogram. G is 9.81. S is 1 meter. So everything was provided. So even you examine clearly the units here, this will be cancelled out. This will be cancelled out. Okay. Take note, this is energy. So this will be Newton meter, and this is Newton, and this is meter. So therefore, this is a unitless. Take note, coefficient of friction should be a unitless. So it happens only if the units are consistent. So in this case, the units are consistent because everything are done with SI. So calculate using calculator. We have the result 0.4077. This is the coefficient of kinetic friction. This is the answer to the problem. Okay, so I think that's all. Thank you for watching this video. See you.